Newman projections are a really good way to look at the relationships of the atoms attached to two carbons. And here I've drawn a representation using the Newman projections of butane. We're looking along this carbon-carbon bond, and carbon 1, the first carbon that we come to, carbon 2 of the butane molecule, but the first carbon we come to has the methyl group sticking up, and that's the one I've written in light blue in the Newman projection. And the carbon we come to next has the methyl group sticking down. So this is butane. Here's a Newman projection of butane that shows one of the possible relationships of the atoms attached to one carbon relative to the atoms attached to the other. And because there's completely free rotation around that sigma bond that holds the two carbons together, these atoms can develop any relationship with respect to each other that you could imagine. There's literally an infinite number of possibilities. But what we do when we analyze these conformations, and conformations, there's our word, is a specific spatial arrangement of atoms. When we analyze the conformations, we tend to look at the ones that are highest energy and the ones that are lowest energy, the two extremes. And then we could extrapolate between those if we need to. I've written here, as a Newman projection, the lowest possible energy conformation for butane, considering that carbon 2, carbon 3 bond that we're looking down. It's a conformation that we call staggered because the atoms on one carbon are as far apart as possible from the atoms of another. So these atoms, this hydrogen is right smack in the middle in the space between the CH3 and the H. And there's a special relationship between the two methyl groups. One sticks straight up and one sticks straight down. I'm going to point out those two sticking straight up and straight down, and when that's the case, we say that they have an anti-relationship to each other. Now, if we take a look at this molecule and think of holding the atoms on one carbon still and rotating the other, we could picture this hydrogen moving in this direction, this methyl moving in this direction, and this hydrogen moving in that direction. In other words, the dark blue ones are moving. They're attached to the back carbon. And the light blue ones are being held still. They're attached to the front carbon. And if we rotate 60 degrees, and look at what we have now. We've moved those blue atoms around to the point where they are straight across from the atoms attached to the other carbon. This is a conformation that we call eclipsed, when the atoms are directly across from each other. And it's a higher energy conformation. It's a higher energy conformation because we have brought those bonds closer together. And that causes an interaction that is not possible when those bonds are further apart. But it turns out that this is a higher energy conformation, this eclipse conformation. And the increment of energy that's added is called torsional strain. Torsional because it's has occurred because we've been twisting turning one carbon relative to the other as we rotate about that C2-C3 bond. So this is higher energy owing to torsional strain. Keep rotating those atoms in the back. Another 60 degrees. We'll get to another staggered conformation. But this one is different from that one, isn't it? In this one, the two methyl groups are no longer anti, but rather they have a special relationship which is called gauche. They're not eclipsed with each other, but they're still too close. So there is some strain developed because those two methyl groups are closer to each other. It's a French word, gauche. So it's a staggered conformation, but it's higher energy than the one I showed you to begin with. And now that higher energy is not because we brought bonds closer together, but because we brought atoms closer together. Those atoms are attempting to occupy the same space. So this methyl group and this methyl group are bumping into each other. And that's a spatial interaction that increases the energy, and that's called steric strain. Now we can continue our rotation another 60 degrees, and there goes that methyl group. And we get to another conformation where the methyl groups are directly across from each other. The hydrogens are across from each other, and the other hydrogens are across from each other. So this is another eclipsed conformation. And now we have the bonds interacting in torsional strain and the methyl groups interacting with steric strain. And so this is the highest energy conformation. Has both torsional strain and steric strain. Now we could rotate another 60 degrees. Holding that front one still, we'll move the back one, those dark blue ones. And get another conformation. This one again has the gauche relationship. It will be staggered, like this one, but it still has some steric strain because of the interactions here. In fact, this conformation and this one are identical, aren't they? Except that they're just reflected into each other. And we'll notice that it's gauche, and it has steric strain. And so these two guys are the same energetically. Rotate one more time. To make a sixth conformation. It's eclipsed. That it will experience torsional strain and the energy is just like this one. So the Newman projection analysis of butane, looking at the C2-C3 bond, shows us 3 eclipsed conformations and 3 staggered conformations. The eclipsed conformations are higher energy, and of the staggered conformations, 2 are higher energy than the very lowest one. And of the eclipsed conformations, 1 is the highest energy of all, and that's where the methyl groups are eclipsed. So the conformation experiences both torsional strain and steric strain. And these conformations will be important with respect to some kinds of reactions that we talk about. And as we do the conformational analysis, we'll want to notice whether the conformation required for reaction is higher energy or lower energy. So the Newman projection is a very valuable tool in understanding the conformations that lead to chemical reactions.